Welcome back to the next session of Design of Pre-Stressed Concrete Elements course. So from the last session, we were doing or discussing problems or analysis of composite section. In that, I have been discussed one particular analysis or a problem. In that, we have been analyzed or calculated the resultant stresses of a composite section for a proper case and for an unproper case if or assuming the modular ratio is same. We will move on to the next problem. In this session, I am going to teach you if modular ratio is different. If the modular ratio is different, what will be the change in the analysis or what will be the change in the problem? Okay, let us go ahead. So let me take a problem. So in this particular analysis, I am going to take a different section so that it will be helpful for you also in order to calculate the sectional properties. Because in the last problem I have been considered the T section. In that precast pretension is also rectangle and cast density is also rectangle. So in this particular problem I am also going to change the section. Okay, so let me go ahead. So now a composite bridge deck of span 12 meter is made up of a precast pre-stressed symmetrical I section. Precast pre-stressed symmetrical I section and an in situ cast slab and an in situ cast slab. Okay, so now the composite section is made up of these things. Now the precast I section, okay, are spaced at 750 mm center to center. Okay, and the top, let me place center, and the top of, okay, and the, not top slab of, so that will be more okay, familiar word, top slab of the in situ concrete, top slab of in situ concrete is 120 mm thick, full stop. The cross-sectional details of precast section are as follows. So he has given the data of precast pre-stressed section. So let me know that. So the thing is the thickness and the thickness of top and bottom flange, equal to 110 millimeter, width of top and bottom flange equal to 200 millimeter. Okay, 200 millimeter. Next, one sec. Yeah, and thickness of web 75 millimeter Next, depth of precast I-beam, that means overall depth. Overall depth of precast I-beam, because it is a I section, hence I-beam equal to 500 millimeter. Next, self-weight of precast, this is a very important thing. So they have been given the unit weight or the self-weight of a precast concrete. So in which we need to consider self-weight of precast concrete equal to 24 kilonewton per meter cube and self-weight of cast in situ equal to 23.5 kilonewton per meter cube. Next, the pre-stressed beam is supported during, this is a very important statement, the pre-stressed beam is supported during the placing of in situ concrete. During the placing of in situ concrete. So the formwork which have been provided, the formwork is estimated as 0.2 kilonewton per meter of the span Next, if the compressive pre-stress in the beam, is 15 Newton per millimeter square, at the bottom and 0 at top, full stop. So for this, calculate the maximum stresses, developed in precast and cast in situ slab, under an imposed load of 5 kilonewton per meter square. And the very important thing they have been highlighted here is, assume the modulus of elasticity of concrete. I will write here on the top. Assume the modulus of elasticity of concrete. For precast as 1.25 times the modulus of elasticity of cast in situ slab. So this is the problem they have been given. So first I will tell you what will be the change in the problem from last problem what we did and to this problem what we are doing in this particular session. So now coming to the problem. So first thing, it is a composite bridge deck, made up of a span 12 meter, which is made up of precast pre-stressed symmetrical I section. So in the last problem I have been considered the rectangular section, but in this particular problem I have been considered the I section. Okay, and the next, the same in situ cast slab, no change in this. And the next, this precast I section are spaced at 750 mm center, fine. And the top slab of in situ concrete is 120 mm thick, okay, which is 120 mm thick. And the next, they have been given the cross-sectional details of the precast section, that is thickness of the top and bottom flange, width and bottom flange, thickness of the web, okay, depth, everything. So these are the, okay, sectional properties, or I can say is not dimension parameters. Dimensional parameters of precast pre-stress symmetrical I section and cast in situ slab. Now, immediately the question arises whether I need to go ahead for propped case or unpropped case, because as I discussed in the last class, the composite section analysis will vary depending upon whether it is propped case or unpropped case. Okay, so based on that, in the last problem I have been given this directly, okay, directly propped and unpropped case. In this particular problem, okay, I have not been mentioned, okay, whether it is propped case or unpropped case. So how to identify that? Okay, you can see here indirectly they have been given, okay, the pre-stressed beam, okay, the precast pre-stressed beam is supported during the placing of concrete. Please note this point. The precast pre-stressed beam is supported during the placing of in situ. What it indicates? It indicates it is propped section. It indicates it is a propped section. Okay. So now whatever I am going to do the analysis of composite section of this particular problem, I am going to do or perform the analysis as per propped construction case. Okay. So now in this particular problem, instead of mentioning it is propped, okay, they have been given it is supported. So I think I have been discussed in the case of okay, the behavior or when I was explaining propped case. Okay. So propped means I am going to support the precast. So I am going to support the precast pre-tension or pre-stressed beam, okay, while placing the cast in situ slab. Okay, so for this particular case, you know what will be the change in the problem. That is the one thing. And the next thing, in this particular problem, they have also been given the formwork load, which I need to consider. Okay, formwork is estimated. It means the load induced by the formwork as 0.2 kilonewton per meter. Okay, in the last problem, okay, I have not been given this load. Okay, so in this particular problem, they have been mentioned the formwork load as 0.2 kilonewton per meter of the span. Okay, this is the extra, okay, stresses apart from precast. Okay, the stresses due to the precast, stresses due to the cast in situ slab, stresses due to the composite section. Okay, the one more stress I need to consider is formwork stresses, that is stresses due to formwork. Fine. Next, so in the last problem I have been given pre-stressing force has been induced of so and so magnitude. Am I right? But in this particular problem, they have directly given the pre-stress, the compressive pre-stress that has been developed in the composite section at the bottom. Did you get my point? In the last problem, I have been given the pre-stressing force. Okay, from those pre-stressing force, used to calculate what will be the initial pre-stress. Am I right? So in this particular, you need not to go ahead with that. So directly they have been given compressive pre-stress in the bottom is 15 Newton per millimeter square and 0 at the top. Did you get my point? And one more thing, in the last problem, I have been given loss of pre-stress. Okay, so at that particular instance, you need to go ahead with effective pre-stress. But in this problem, they have not been given anything like loss of pre-stress, hence you need not to worry about that. So initial pre-stress will come into the picture, no effective pre-stress will come here. Is it clear? Next. So now these are all the data they have been given, okay, and these are all the conditions they have been given. Okay, so for this condition, calculate the maximum stresses developed in precast, pre-tension or pre-stressed beam and cast in situ slab, okay, with the main condition assuming the modulus of elasticity for precast as 1.5 times the modulus. Now, practically what I want to specify is, as I stated, since the grade of concrete of cast in situ slab is less as compared to the precast pre-stressed beam, automatically because of variation in the grade of concrete, the modulus of elasticity will also vary. Is it clear? So usually the modulus of elasticity of a cast in situ slab will be 25, okay, kilonewton per millimeter square, and coming to the modulus of elasticity of precast pre-tension beam, it will be what I can say 38 or in between 25 to 38 kilonewton, 25 to 40, sorry, 25 to 40 kilonewton per millimeter square. So this will be the modulus of elasticity. The ratio of this will be 1.25. The ratio of the cast in situ and the precast, okay, will be 1.25. Okay. So now in the last problem, okay, it was same. That means it is equal to 1. Okay. Now in this particular problem, it is not equal to 1. It is 1.25. The ratio is 1.25. Okay. Now for propped and modular ratio change, so how to go ahead with the problem? So let me go ahead. So for this, how to go ahead with the analysis. So first let me draw the section, okay, how it looks. So now let me draw this I section because they have been clearly mentioned. One sec. So now, so in the last problem it was a rectangular section. Now the precast pre-stress section is a symmetrical section. It is a symmetrical section. Okay. So let me hatch this. Okay. So now they have been given this dimension whose dimensions are 200, 110, this is also 200, 110, okay, because it is a symmetrical section, and now this depth is 75 and also he has given the overall depth. The overall depth is 500 millimeter. Fine. So this is the precast pre-stressed I section dimension. So now on this, okay, I have been placed the cast in situ slab. I have been placed the cast in situ slab of thickness 120 mm thick. Okay. So I have been placed a cast in situ slab of 120 mm thick. Okay. And so as they have been clearly mentioned 750 mm centers, so the dimension is 750 mm. So this dimension is 750 millimeter. Okay. Fine. So let me go ahead. Okay. So this is the thing. Okay. So this is a cast in situ slab. Cast in situ slab. And this will be precast. So now let me recall whatever we did. So now I need to calculate the stresses for composite section for propped case. Am I right? So now what are all the things I need to do? Now I need to calculate stresses due to the self-weight of the precast pre-stressed beam. Next, stresses due to the self-weight of the cast in situ slab. Next, stresses due to the live load on the composite section. Apart from these three, one more thing, stresses due to the formwork. So these four stresses I need to consider. How I need to consider? So let me go ahead. So first step is stresses due to self-weight of precast pre-stressed beam. Stresses due to the self-weight of precast pre-stressed beam. Okay, so how to go ahead with this? As usual, calculate the first area, all those things. So that is 200 into 110. Okay, multiply by 2 because top and bottom flange both are same, plus 75 into, you know, the web width. Okay, and the dimension of this is 280. Okay, so that is 500 minus 220, it will become 280. So 75 into 280, so which is equal to 65 into 10 to the power of 3 millimeter square. Next, so this will be the cross-sectional area. Next, moment of inertia I. So as I stated, so when the symmetrical I section comes, okay, you can divide this into 3 rectangles and you can solve. Okay, or else you can directly consider this as rectangle. Okay, this as a total rectangle, that is 200 into, okay, 500. Okay, that is BD cube by 12, 200 into 500 cube by 12. Okay, in that I need to deduct this portion, this. Okay, so this portion, I need to deduct these two rectangles. Am I right? So I need to know this dimension. So in the total moment of inertia, deduct this moment of inertia, you will get the moment of inertia of I section. So that is what the concept. So now the BD cube by 12 minus, okay, so what will be the dimension of this? So 200 minus 75, okay, 200 minus 75 divided by 2. So that will be 62.5. So this dimension is 62.5. Am I right? So 62.5. So hence 62.5 into 280 cube by 12. So how many rectangles are there? 2, hence I will multiply 2. So like this I need to calculate. So the answer will be 1.855 into 10 to the power of 9 millimeter to the power of 4. So this will be I. Okay. Next, coming to the ZT and Z bottom, I think it will be same. Okay, or it will be same because it is a symmetrical section. So hence I divided by Y bar, so which is 1.855 into 10 to the power of 9 divided by 250. So therefore, so the answer will be 7.42 into 10 to the power of 6 millimeter cube. 7.42 into the power of 6 millimeter cube. Okay. Next, the same thing what we did, self weight of precast section. So that is WD1, which is equal to, okay, so you already know which is in millimeter square. Okay, so hence 65 into 10 to the power of 3 divided by 10 to the power of 6, okay, into 24, because you want the answer in kilonewton per meter, but your area is in millimeter square. okay, and the density will be in kilonewton per meter cube, hence you need to manipulate this. So hence 1.56 kilonewton per meter, 1.56 kilonewton per meter. Next, moment due to self weight, okay, so that is MD1, which is equal to WD1 into L square. So as I stated, if they have not been mentioned where you need to calculate the stresses, so automatically, okay, by default you need to calculate the stresses at mid-span section. So hence WD1 into L square by 8, so that is 1.56 into 12 square divided by 8, okay, which is equal to 28.08 kilonewton meter, 28.08 kilonewton meter. Okay, next, stresses, okay, due to self weight of precast, okay, for this at top, which is equal to MD1 by Z, okay, at bottom, which is also same, MD1D by ZB. So that is 28.08 into 10 to the power of 6, because I want the answer in Newton per millimeter square, okay, but the moment is in kilonewton meter, substitute in Newton millimeter, then divided by Z top, 7.42 into 10 to the power of 6, okay, the same thing, okay, both in the top and bottom, okay, that is 3.78 Newton per millimeter square. So 3.78 Newton per millimeter square. So both the top and bottom, it is same, because the ZT and Z bottom are same. So like this, we need to calculate the stresses due to the self weight of the precast, okay, pre-stressed section. Okay, next, so let me move on to the next. So the next is, okay, I need to go ahead with a calculation of stresses due to the self weight of cast in situ. Am I right? Okay, so when I want to go for this, okay, first you need to decide whether it is propped and unpropped. Why? Because, so when it is, so now in the problem they have been given propped case. Okay, so now if you want to calculate the stresses due to the self weight of cast in situ slab, then you require the sectional modulus of composite section. Am I right? Because when they are going to prop, okay, automatically I need to consider the overall dimension of a composite section in order to get the stresses for self weight of cast in situ slab, what we did in last class or last session. Okay, so hence, so instead of going to the stresses due to the self weight of cast in situ slab, what I am going to do now is, first I will calculate stresses due to the live load on the composite section. Am I right? Okay, so there the problem will become simpler. Did you get my point? Because clearly they have been mentioned propped case. So now if you want to solve for a propped case, or if you want to calculate the stresses for self weight of a propped case, cast in situ slab case, then you require the dimension of a composite section. So hence, what I am going to do here is, first I will calculate the stresses due to the live load on the composite section. Live load on the composite. Because without knowing the dimensions of this, I cannot calculate, or I cannot go ahead with this, okay, the calculation of stresses for cast in situ. So now, the very important thing, okay, when I am going to do or calculate the stresses due to the live load on composite section, so at this particular instance, okay, so what I am going to do here is, the modular ratio is 1.25. Modular ratio is 1.25. So for this 1.25 case, how to go ahead with this problem? So now the change in the problem or change in analysis, will come here. So now as usual, first, you calculate the area of cast in situ slab and the area of precast. So let me go ahead. So separately I will cast. So area of precast. Anyway it is not required, but I will calculate this. So we already calculated area of precast is 65 into 10 to the power of 3 millimeter square. Next, area of cast in situ equal to so that is 750 into 120 millimeter width into thickness. So which will be 750 into 9 into 10 to the power of 4, 9 into 10 to the power of 4 millimeter square. So this is the area of precast and area of cast in situ. Next, the very important thing, centroidal axis for composite section. Now consider the entire thing and calculate the y bar. So when you go into calculate the y bar for a composite section, so you need to consider the reference axis. So now I am going to calculate the y bar or a centroidal axis for composite section from top. So this will be the reference axis. So considering this as a reference axis, so let me go ahead. So now y bar t. So how to go ahead with this? So that is 750 into 120, so that is area 1, 750 into 120, multiply by 60. Why? Because from the reference axis it is 120 by 2, therefore into 60. Next, so now the very important thing, area of precast 65 into 10 to the power of 3, multiply by, the y2 of this precast measured from top. Now this is y1, now this will be y2, exactly at the center it will be y2. So how to calculate that? 500 divided by 2, because it is symmetrical section, 500 divided by 2, that is 250 plus 120. How much? 250 plus 120, because I need to consider the y2 from the top, that is the reference axis. So 250 plus 120, how much? 370. So into 370. So now for this I need to multiply this modular ratio for this precast section. So I need to consider the modular ratios. I think this will be very better, into 1.25. So it will be no confusion. So this will be for the cast in situ and this will be for the precast. So now for a precast area multiply by y1, I need to multiply the modular ratio. So please be careful. Put a star mark here so that you will be knowing. Next, divided by a1 y1 plus a2 y2 divided by a1 plus a2. So now once again, what is your a1? So 9 into 10 to the power of 4, no change, plus a2 65 into 10 to the power of 3 multiply by 1.25. Once again I need to multiply the modular ratio for the precast. So for this, so let me substitute everything in the calculator. I hope you understood. So this 1.25 modular ratio I need to consider for the wherever the precast section will come. This is A1 Y1, A2 Y2, A1 plus A2. Wherever this A2 and this terminology will come, I need to multiply this modular ratio 1.25. Did you get my point? So for this, the answer will be 207 millimeter. So 207 millimeter. So this will be your YT. Okay. Next, coming to the moment of inertia. Moment of inertia. So how to calculate the moment of inertia? The same thing. Okay. Now moment of inertia of the first section about the centroidal axis, that is cast in situ. But precast we need to consider individually. Okay. Hence, moment of inertia of the second section about the centroidal axis, moment of inertia of the third section about the central axis, moment of inertia of the fourth section about the central axis. So hence 1, 2, and this will be 3, and this will be 4. So 4 rectangles. Okay. So I think in basic elementary class you people have did. Okay, the same thing I am going to repeat here. Okay. So now first let me consider this. Okay, let me go ahead with the first I1XX. So 750 into 120 cube by 12 BD cube by 12 plus, okay, B into D, that is 750 into 120 into Y1, that is 60 minus 207, okay, 207 whole square. Yes, it is 207. So this will be your moment of inertia for a precast. I will repeat, BD cube by 12 plus B into D multiply by Y1 of the first section, which is 120 by 2, 60 minus, okay, Y bar whole square. Like that, I will go to the second section. So which is the second section is this one. So that is 200 into, okay, put a flower bracket here. Okay, I will tell you why I need to put a flower bracket. Okay, so 200 into, and open the small bracket. Okay, 200 into, or square bracket, 200 into 110 cube by 12 plus 200 into 110 multiply by Y2. Y2 is how much? That is not this Y2. Okay, now Y2 of this, that is 110 divided by 2 measured from the top. That is 120 plus 110 by 2. 120 plus, okay, 110 by 2. Okay, so that is 175. Okay, 175. Okay, minus 207 whole square. So this is your height 2. Okay, 175 minus 207 whole square. Okay, that is 120. Okay, plus 55, that is 175. Next, we will move on to the next. Plus 75, this third section, 75 into 280 cube by 12, BD cube by 12, plus 75 into 280, okay, multiply by Y3, that is 280 by 2. 280 by 2, 140 plus 110 plus 120. Okay, because I need to measure from reference axis. So totally it is 370. So 370 minus 207 whole square plus, so go to the fourth section, 200 into 110 cube by 12 plus 200 into 110, okay, multiply by Y4, okay, that is 120 plus 110 plus 280 plus 110 by 2, 110 by 2 plus 280 plus 110 plus 120. So totally it will be 565, okay, 565 minus 207 whole square, okay, that is one thing. Now the very important thing what I need to do here is multiply the entire thing, that is the moment of inertia of the precast I2, I3, I4 with a modular ratio 1.25. So this is very, very important. Okay, so what I did in Y bar calculation, okay, the same thing, okay, I need to do here. For the entire moment of inertia of the precast, that is second, third and fourth, I need to multiply the modular ratio 1.25. Did you get my point? Okay, so after multiplying this and after substituting in the calculator, you will get 6.51 into 10 to the power of 9 millimeter to the power of 4. 6.51 into 10 to the power of 9 millimeter to the power of 4. Okay, so, okay, like this, okay, you need to calculate the moment of inertia. You need to be very careful. Okay, I need to multiply the modular ratio 1.25, okay, for the moment of inertia of the precast section. Next thing. Next is, we'll go with the, okay, that is calculation of this live load. Okay, let me go ahead with the live load calculation. The live load on the composite section will be, okay, so the live load on the composite section will be, okay, which will be 0.7, okay, 0.7. No, first let me calculate, Z, okay, because we require Z. Zt is equal to I by Yt. So once again, okay, Y top and Y bottom will change because since you are calculating for a composite section, automatically Y top and Y bottom will change. So Y top is 207. So automatically if you want Y bottom means out of 720 minus 207. So that will be your Y bottom. 720 minus 207. Almost I can say 3, then 1, then 6 to 5. So this will be your, that is 513 mm. Okay, I hope it is correct. 7, 3, 10, 1, 2, and then yeah, Y bottom will be 513 mm. Okay, so now Y top, substitute that. So you know 6.5 and 10 to the power of 9 divided by 207, you will get 3.14 into 10 to the power of 7 millimeter cube. 3.14 10 to the power of 7 millimeter cube. Next, Z bottom, I divided by Y bottom, okay, which is equal to 1.57 into 10 to the power of 7 millimeter cube. So please substitute properly. So that is Zi, you know, 6.5 and 10 to the power of 9 divided by Y bottom 513, you will get 1.57 10 to the power of 7 millimeter cube. Okay, so this is regarding your thing. Next, we have calculated area, we have calculated Y top, Y bottom, we have calculated I, we have calculated Z. Next, we will move on with the next thing, that is WL. Okay, we need to consider WL. Okay, because we don't know what is the WL. Okay, let me go ahead. So that is live load on composite section. Okay, here also the same thing. Okay, what we did in the last, okay, we need to consider. So when the live load, that means when the composite section is subjected to the live load, means we need to consider the dimensions of the cast institute, because I need to subject the live load on the composite section only on the top of a cast in situ. So hence I will consider the dimension of a cast in situ slab. Please note down. So while calculating the live load on the composite section, I will consider the top surface of a cast in situ. That means those width and length, okay, multiply by the load given. So that is 0.75, okay, will be the width, okay, multiply per meter length into 5 kilonewton per meter square. So which will be 3.75 kilonewton per meter. So this will be your WL. So for this, moment due to the live load, moment due to live load, which is equal to same thing WL into L square by 8 which is 3.75 into span is 12, okay, into 12 square by 8, okay, which will be 67.5. So ml is equal to 67.5 kilonewton meter. Okay. So now for this, let me calculate the stresses. Okay. So now stress at top and bottom will change. So please know, okay, be careful because YT, Y bottom has changed, and ZT, Z bottom will change. Automatically the stresses will also change. So stress at top, that is, okay, ML divided by Z top, okay, that is 67.5 into 10 to the power of 6 divided by 3.14 into 10 to the power of 7. Next, stress at bottom, which is, okay, ML divided by Z bottom, that is 67.5 into 10 to the power of 6 divided by 1.57 into 10 to the power of 7. So the answer will be 2.14 at top, 2.14 Newton per millimeter square at the top, and then 4.29 Newton per millimeter square at the bottom. Okay, so like this, you need to calculate the stresses due to live load on the composite section when the modular ratio is not same. Please be careful, when the modular ratio is not same, you need to be very careful. You need to multiply that modular ratio while calculating Y bar and also while calculating the moment of inertia. Did you get my point? Okay, so this is very, very important. So you need to be very careful while calculating the stresses due to the live load on the composite section. So let me move on to the next. Okay, so now we can easily go ahead with the calculation of stresses due to the sulfate of cast in situ. Because we know the dimensional parameters of composite section, okay, we can easily go ahead with the stresses calculation. So now let me go ahead. So the next step number 3 is stresses due to self-weight of cast in situ slab. If it is unpropped one, okay, I would have not required this. Okay, first I will calculate that and then I will go with the composite. But because of this propped case, first I need to know the composite section dimension, then I need to calculate the stresses. Okay, so now let me go ahead with this. Okay, so now coming to this WD2, okay, that is what I can say the sulfate of in situ concrete slab, sulfate of in situ concrete, sulfate of in situ concrete, that is WD2. WD2, okay, which is equal to, okay, 0.75 is the width, 0.12 is the thickness, multiply by the density. So please be careful, in the problem they have been given the cast in situ sulfate as 23.5. So please be careful. Okay, while in the precast also we have been considered 24, okay, without knowing, but please be careful. So now it is 23.5, hence multiply that 23.5. So when they have not been mentioned anything, you can consider 24 or 25. But in this problem, they have been given 23.5. So WD2, okay, which is equal to, okay, so how much it is? 2.115. 2.115 kilonewton per meter. 2.115 kilonewton per meter. Next, so for this, moment due to self-weight, okay, which is MD2, which is equal to W2 into L square by 8. okay, WD2, okay, into L square by 8. So that is 2.115 into 12 square by 8. So which will be, the answer will be 38.07 kilonewton meter. Now coming to the stresses at top. Okay, you already know, okay, while placing the precast concrete slab, okay, well, they are going to prop this. That means if the precast pre-stress section will be propped while placing the cast in situ slab, we need to consider the overall dimension of the composite section. So hence, okay, stresses at top is equal to, okay, MD2 divided by Z top, okay, MD2 divided by Z top. So that is 38.07 into 10 to the power of 6, okay, divided by Z top is how much? 3.14 into 10 to the power of 7. Okay, so that's why, okay, without knowing these sectional properties, we cannot calculate first. So hence first I go ahead with this composite section, later on I can go. But in unpropped case, okay, you need not require this dimension, because this will be the Z top will be the dimension of precast one. Okay, whatever I did in the last problem. Okay, but in this problem, okay, they have been given the propped case. So hence I am going to do like this. So the answer will be 1.21 Newton per millimeter square. Next, at bottom MD2 divided by Z bottom, MD2 divided by Z bottom, which is 1.57 into 10 to the power of 7, 38.07 into 10, okay, 10 to the power of 6 divided by 1.57 into 10 to the power of 7. So the answer will be 2.42 Newton per millimeter square. So this will be the stress at top and bottom for self-weight of cast in situ slab. Okay. Next, okay, apart from this, okay, he has also given one more thing, okay, that is stress due to the formwork. Okay, so this is the one more additional thing he has been given in the problem, so which I need to consider. Stress due to formwork. Okay, stress due to formwork. So how to go ahead with this? So that is, so you already know, okay, what will be the self-weight of formwork. So they have been given, I think, yeah, they have been given as 0.2. So write down that self-weight of formwork is equal to 0.2 kilonewton per meter. So hence moment due to formwork equal to, okay, 0.2 into 12 square divided by 8. Okay, so 0.2 into 12 square divided by, which is 3.6 kilonewton meter. 3.6 kilonewton meter. So for this stresses, okay, so let me calculate the stresses. Okay, so the same way at top and at bottom. So now it is very important. So which Z I need to consider? So now since I am going to support, okay, so since I am going to support what I can say, the precast, okay, so the precast dimension in which we have got, we need to substitute that. So that dimension are, okay, so those dimension are One sec. So what we got is stresses, okay, due to formwork at top 1. So okay, so what we got here is 7.42. One sec. Let me check out the answer. Yes, 7.42. Yes. Yeah. So that is Z top and Z bottom of precast, because that's what I have already been told. Okay, since okay, we have been supported the precast pre-stressed section. So since we are providing a prop to this section, okay, so hence it will be like this, M divided by Z. So that is 3.6 into 10 to the power of 6, and Z will be the dimension or sectional modulus of precast. So which is 7.42, okay, which have already been calculated, into 10 to the power of 6, okay, which is 0.48 Newton per millimeter square. Okay, at bottom also which is same, no change, okay, because Z top and Z bottom both are same, okay, so therefore 0.48 Newton per millimeter square. Okay, so this will be the stresses at top and stresses at bottom. Okay, so like this we need to calculate, or we need to go ahead with the calculation of stresses. Hope you have understood the problem clearly. Okay, so in this problem they have not been mentioned whether it is propped or unpropped. So since they have been mentioned, okay, the precast or pre-stressed beam is supported during the placing, okay, which clearly indicates it is a propped case. Okay, so that is the one thing. And the next, they have been given additional formwork load we need to consider. And the next, the modular ratio is not same. The modular ratio is not same. Okay, it is 1.25. Okay, for this particular problem, okay, what changes is from the last problem is, the one thing is, okay, when you come across with a propped case, okay, we need to go ahead with, okay, that is stresses due to self-weight of cast institute slab calculation with respect to the sectional properties of composite section. That means that Z top and Z bottom we need to consider, okay, the composite section for the case of stresses due to the self-weight of cast institute slab when you are going to calculate the stresses for propped construction case. That is one change. And another change in the problem what have been solved in this here is modular ratio. So now while calculating, or when, okay, when I need to consider this parameter, that is 1.25. So while calculating the live load, that is stresses due to the live load on the composite section, at that particular instance, okay, while calculating the Y bar, while calculating the Y bar, okay, Y top, moment of inertia, okay, in all those things. So okay, in the precast dimension, or in the precast area, we need to multiply this 1.25 modular ratio. Did you get my point? Okay, so this is the change in the problem from last problem whatever we solved to this problem. Okay, so like this we need to go ahead with the analysis. So after this I will draw the, what I can say, the stress diagram. Okay, so that okay, we'll know. So we'll also draw the stress, because stress diagram is very, very important. Okay, you need to draw the stress diagram. Okay, so let me draw that. So first write down that I section. Write down that I section. Okay, on above that place a cast in situ slab. Okay, so this is the thing they have been given. So let me one by one draw the stress diagram. Okay. So now, first thing, so as I stated, okay, initial pre-stress. So in the problem, they have been given the initial pre-stress as, okay, 0 at the top, okay, 15 at the bottom. Okay, so let me write down that 0 at the top, 15 at the bottom. Okay, in the last problem, apart from initial pre-stress, okay, they have been given the loss of pre-stress. Okay, therefore we have considered effective pre-stress in the last case. But in this problem, they have not been mentioned anything like loss of pre-stress, hence I will consider this initial pre-stress itself. Next, stresses due to the self-weight of precast pre-tension beam, which is how much? 3.78. Okay, so let me draw that. So what is positive, negative? How much? 3.78 at the top, 3.78 at the bottom. Why these two will not change? Because it is a symmetrical section. In the last problem also, it was a rectangular section which is symmetrical, hence both these two will also same, a top and bottom. If this is an unsymmetrical one or any T section, then automatically these two things will change, a top and bottom. Did you get my point? Next, okay, plus stresses due to the self-weight of cast in situ slab. Okay, so as I stated, okay, you need to draw or consider like this. So how much? So this dimension is 1.21 and then 2.48. This is positive and this is negative. Okay. 2.42, sorry, 2.42 and this is 1.2. Next thing is stresses due to the live load on the composite section, which is 2.14 and 4.29. Okay, so stresses due to the live load on the composite section 2.14 and 2.14, and the next is 4.29. This is negative 4.29. Am I right? Okay. And the next is, okay, stresses due to the formwork. So this will come in the case of precast. Okay. So that is, so positive, negative, 0.48, 0.48. Okay. So now, so write down the resultant stress. Okay, so for this, you need to calculate resultant stress. So for that, so as I stated, you need to calculate this, okay, things, okay. Then it will be something like this, 2.14 plus, this will be this one, 2.14 plus 1.21, okay, this will be this, okay, then automatically, so this, okay, will come like this. Okay, so this indicates yellow color thing and this indicates the white. So the white is how much? 0.48 plus 3.78. So this will be white. Okay, next. So this finally, so this will be your final thing. So like this you need to calculate. Okay, so these two things will be this. So this will be 0 plus 3.78 plus 0.48 will be this. And finally coming to this, 15 minus 3.78 minus 2.42 minus 4.29 and minus 4. Obviously it will be positive and this will be that value. So this will be the resultant. So let me write down. Okay, initial pre-stress. Okay, this will be stress due to self-weight of precast. This will be stress due to self-weight of cast in situ, and this will be stress due to live load on the composite section. Next, this will be stress due to formwork, and the final thing will be resultant stresses. Resultant stresses. So like this, we need to go ahead with the problem. So this is the way you need to analyze the composite section, okay, for propped case and unpropped case, when the modular ratio is same and when the modular ratio differs. Okay, so by this I completed one particular topic in this composite section. Okay, I hope you have understood the things. Okay, please be careful while solving, okay, and while substituting the things. So please understand, please read the problem, whether they have been given a propped and unpropped, okay, based on. So from these two things or from this concept, you will get a one question in the examination. One question you will get the examination of 20 marks. Did you get my point? So it is very easy, no need to get burdened, okay, it is very easy. Just, okay, you need to recall the things, okay, based on that you need to substitute the concept, okay, do this. Because the same thing, okay, what we did in module number 1. Same thing. So there also you did EA calculation, I calculation, Z calculation, W calculation, moment calculation. Okay, here also you are doing the same. But the thing, okay, you need to use the concept properly and you need to calculate. That's it. You are not using any extra formula, you are not using any extra concept. Okay, the concept, okay, whatever the calculation you have done in the module number 1, same I am going to do here also. But just a propped and unpropped case I will introduce here. Did you get my point? Okay, so there I used to do only for I section, T section, rectangle, something like that. Here the combination of these two, combination of two sections. So that is what the change from module number 1 to module number this. Is it clear? Okay, I hope you have understood the things, okay, what have been done, okay, from the last session and in this session regarding the analysis. So we will continue with a few more topics like deflection of composite section, okay, in the next session. So thank you for listening.